Yeah. So it gives me enormous pleasure in introducing Professor Patrick Polo from Sorbonne University, Paris. He's going to spend a month here sharing his insights into the SGA3. Let me say a few words about this whole concept of SGAs and EGAs. There was a period of from 1950s to 1970s, which might be called the dream period of mathematics, nothing less than the Renaissance in European art, I think, where masterpieces were created, which included some of the Semina-Bourbaki notes, the EGA, and then finally the SGA, culminating sometime in almost in late 60s. And of this, there were people who were, I think, as Deline puts it, there was the central architect of the Grothendieck, and others were simply the, who were bringing pieces to fit into this superstructure. And there were some people had tremendous insight into those times. And things were written down on almost perfect shape. But I think as time went by, I think they needed adaptation to several developments which took place in modern and the same subjects. And a few very dedicated people in Paris, and got together to some sort of revisit some of these texts and make it amenable or accessible or maybe enjoyable, with also the connections to the modern developments for modern audience. And from Paris, who I think perhaps, apart from the early masters of the subject, in the modern subject, perhaps has one of the deepest insights into this whole story of SGA3. And so it's one of the real special pleasures to have him share with us his insights into the subject and make us some sort of have at least a second-hand participation in this great work of art called SGA3. So this is Patrick Polo here. So we're going to have 2 lectures a week, and only for next week, because of Tuesday being the 15th of August, our lecture will be on Wednesday and Thursday. And maybe we'll have one extra lecture during the month to take care of the one missed lecture, which was supposed to be on Tuesday. So Patrick Polo.
Okay, so I'm very pleased to be here at the invitation of Professor Balaji. And so, as he said, I worked with another colleague, Philippe Gilles, on the new edition of SGA3. So SGA means Séminaire de géométrie algébrique. SGA. So this was a seminar run by Grothendieck at the beginning of the 60s. It was a yearly seminar. So the first one was about etale morphism and Galois theory. SGA2 was about local cohomology. SGA3 is about group schemes. So basically, Grothendieck is recording as the sole author of SGA 1 and 2, even though they were exposed by other participants. But so this one was directed jointly with Michel de Mazure. This is under the supervision of Grothendieck, precisely on a reductive group scheme. And so SGA3 comes in 3 volumes, and volume 3 is essentially the de Mazure thesis. Okay. And then there was SGA4, which is about etale cohomology, and SGA5, I think it's LAD cohomology, and so on. SGA6 is intersection theory, blah, blah, blah. Okay, so I worked with Philippe Gilles on the new edition of SGA3. And I was not trained in algebraic geometry, and I was trained in Lie algebras and algebraic groups. So it was a really hard work for me to, it was very difficult for me to start this project. So I didn't, so I had to, so I learned scheme theory basically by doing this work. So so let's say that I have an amateur point of view on all these things, which might be interesting in some cases because as I knew nothing about it, I really wanted to understand every single detail. And it's hard reading because there is a lot of material. Very often in more generalities than needed. So you have to find a way between what is really important and needed for the sequel and the extra generalities that you can leave for later. So I'll try to give what I consider the gist of this book and try to illustrate it by examples. So let me also say something else, that in some sense, SGA3, the main results are, let's say, negative ones, because they tell you that some things do not exist. That is, they start with a very general definition of a reductive group, which is something fiber-wise plus other condition. And then all the work is to prove that finally a reductive group is what you think that it is. That is, it comes by Galois descent from a split reductive group. And so there are many pages that are devoted to proving that something does not exist. So these are the negative results. So I will try not to spend too much time on that. And among the positive results, I think it is the tools that are used, because it was precisely the time where Grothendieck were developing his tools like functor, faithfully flat descent, sheaves for fpqc or fppf or etale topology. And all these things are put to work beautifully in SGA3. And so I will try to illustrate these techniques in some concrete examples. So I think this is, so in this sense, I think that SGA3 is a very good introduction to this subject, which is, of course, there has been a lot of modern presentation, but let me say in an abstract way. So these concepts are introduced for themselves, and sometimes you may wonder, why are we doing all this? And so in SGA3, it was the beginning of the theory. And so the concept, you can see why they're introduced, because they really help you go over difficulty. And so I think that this provides a good motivation to study further these concepts and techniques. Okay, so let's start with something very simple. So let's say that chapter one, whoops, will be called groups of multiplicative I. Okay, so let's start with something easy. So in this chapter, so in this section, so M will denote finitely generated abelian. So first, we consider the group algebra over Z. Sorry. So this is just the free Z module. Which are free basis parameterized by M. And of course, the multiplication is given by the addition in M. So it has a structure of is a Hopf algebra. Which means that there is a co-multiplication map, delta, which goes from this algebra to such element EM is sent to the tensor product, EM tensor itself. So this one is called the co-multiplication map. There is a co-units or augmentation map that goes from the ring to the base ring. And it's defined by taking each base element. And there is also an antipode.
कुठली भाषा करणार?
Which send each element. Okay. So this three maps satisfies the usual axiom of Hopf algebras, which means exactly, this means that the scheme for the spectrum. So let us give it. So let's call D of M. So the spectrum of this ring is a group scheme. So this means also, so that is for any scheme S. So the set, the S valued so the S valued points of the scheme. So by definition, so the S valued points, so this is just the set of all morphism of schemes from S into E of M. It's a group. It's a group. And this is functorial. Okay, so by Yoneda lemma, to give a, well, if you have a scheme, if the set of S points is equipped with a group structure, which is functorial in S, so this gives map at the from, well, so let me call G the scheme. So if you have this functorial definition, then you get the map from G cross G to G And the axiom that this is a group, so this translates in some commutative diagram for the corresponding morphism of schemes. And if the scheme is affine, as it is the case here, this gives, so this is the map corresponding to multiplication. So this is the map corresponding to unit section, and this is the map corresponding to G goes to G inverse. And so the axiom of Pfropf algebra is exactly the axiom of groups translated in this setting. You can write commutative diagrams, but well, it's easy to remember that the axioms that will come from the group structure. So what is this group? In fact, so since this one is it is affine, and so this is the set of algebra homomorphism from the group algebra into the ring of global sections of S. And so to give a morphism from the group algebra into some ring, so for each element M, you have to pick an invertible element. So this is a set of, so this is just a set of so for each M, you have to pick its image, and since it's an algebra map and the multiplication is defined in terms of the group structure, so this is a set of group morphism. So let me write groups from M into the invertible sections. Okay, so that's the definition. So in fact, these groups are very familiar to you, because if we write, so this is a finitely generated abelian group, so it has a free part, plus a torsion part. So if I write it like this, well, then firstly, we see that D of Z of S is just taking the multiplicative, the inversible function of this. And so we see that D of Z is just a multiplicative group GM. And if we take a finite cyclic group, so we see this is just the usual group of roots of unity. So we see that mu and S, we got n roots of unity. And so if we decompose M like this, so we see that this is just so this is just D copies of the multiplicative group and a product of these groups. Okay, so okay, so these are very, very easy groups. And note also, because we might need it, note that, well, actually I've already using this here, so that by definition, this is, so if we have so the D of M plus N, so we see that, so this is just a D of M cross D of M. So actually, well, this is what I have used already. Okay, so we have this formula. Okay, so we see that D of M is as a scheme, it's fine. Flat. It's finitely presented. Course, maybe I should not. Maybe I should not write here. Maybe I should come back to the first. Okay. Well, I will stop here. Okay, so D of M is well, so let me start like this. So this algebra is finitely presented over Z because we see so because with the previous notation, so this is just a Laurent polynomial ring, and so we add indeterminates x1, xf, and we mod out by the idea of x1 and 1 minus 1. It's f to the nf minus 1. And that then, by its definition, is free, is a free Z module. And so we get that this group scheme is finitely presented, and faithfully flat. It's fully flat. Well, no prospects there. Okay, so this is just to start with. Now, for any base scheme, so we define just the pullback. So we define BMS. So this is just this. Okay, and so the so this is a fiber product of a spec Z, but I just so this is just the group scheme obtained by Bay exchange. And so it is again a fine finitely presented facially flats over S. And so what is its function of points? So for any S scheme S prime, so we have dm S of S prime. So this is a set of morphism of S schemes from S prime dm plus s. And so we recover the same. So this is just form schemes of S prime into the FM. And so this is what we have seen before. So this is just form groups of M into S prime. S prime. Okay, so we have this. A formulation of the frontal represented by this by base change. So this is just the restriction of the frontal DNS to S schemes. Okay, so let's take this as a slogan. Yes. Oh, S prime, S prime. Yes. Yes, you're right. Yes. It's thank you. Okay. Okay, so we have so this scheme is nice, and now if we look at this decomposition, so we know that mu n is smooth over the base if only if n is invertible over S. So we say that DMS is smooth over S if only if n if only if the order of the torsion part is invertible. Is invertible on S. Okay. So then one said that definition, the group scheme edge over S is called diagonalizable. If H is almost to DNS for some. Yeah. Okay, so these are the groups we want to study in the first place. So in particular, so if M is a free Z module, then H is isomorphic to a direct product of the multiplicative group, and this is then in this case we call it. This is called a torus, and we call it actually we call this a split torus because in 1 minute we'll see examples of non-split tori. Okay, so the next definition. Yes, I've said everything I wanted. Now a group scheme, group scheme H over S is said to be of multiplicative multiplicative type of type M. Okay, so there are two parts in the definition. So it is of multiplicative type, and I add of type M if the following condition is satisfied. Condition is satisfied if for each point S in S, there exists an affine open neighborhood on U of S and anamorphism U prime into U, amorphism of schemes. So amorphism which has to be surjective and flat and with U prime still an affine scheme such that the pullback by this morphism is isomorphic with this group. Okay, so it's multiplicative of multiplicative type of type M. So if every point has a neighborhood and a surjective flat morphism with U prime affine, such that this group become this nice one after base change. Okay, so we say that. So we can say so we say so that is H is locally in fpqc topology D of M. Okay. And so for the moment, so these are just words. I could say this is property blah, blah, blah. And instead of blah, 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 we say that this property is called locally in fpqc topology. But there is nothing more than that for the moment. We don't have to know what is fpqc topology. We don't even need to know that it is a topology. This is just vocabulary. So the definition is it. So that's locally there exists surjective and flat morphism whose source is affine, such that the group becomes this very nice one. Okay, so this is the most general definition. And among those groups, we are going to distinguish some special ones that are nicer than the other. And so further, we say that H is quasi isotrivial. So let me give, so let's call it the map F. So quasi isotrivial if the F above can be chosen etale. So we restrict to a smaller class of nicer map, and we call this quasi-isotrivial. And further, so further, so this is the first level of further, and further number 2. If so we say that H is isotrivial, which is, well, really isotrivial, not if there exists a map S prime to S, surjective, etale. So just to let me write flat etale. Well, flat is not needed because it's contained in etale, but let me just write it to say. I'm sorry, I didn't get. Yeah, so this is why I put it in parentheses. I wrote it just to make sure that we are not losing an hypothesis. Surjective, etale, finite. That's that. HS prime is the offend. Yep. I'm sorry, I didn't hear you. So the order of the torsion group is invertible on S. Okay, so in the previous example, so this is just the product of the NS. Okay, because the group of nth root of unity is smooth over base if and only if n is invertible over the base. And so this is just and otherwise it is, well, it is still very nice, but it's not smooth. Okay, so we have this notion of quasi-isotrivial, we have this notion of isotrivial, and let me add here the masospecial cases. So the third condition is 3. So we say that H is locally isotrivial, respectively, locally diagonalizable, if each S in S has an open affine neighborhood U such that HU is isotrivial, respectively diagonalizable. Okay. And just one more word of terminology. So if H is of, let us, for brevity, so let me write in the sequel I will write of empty will mean of multiplicative type. So if H is of multiplicative type of type Z to the D, then H is called D-dimensional torus. Okay. So let us give examples. So, example. So, example. So let R let R be a ring. So R to R prime, a map of ring, which is Galwork of ring with group gamma. So gamma is finite. So it's a group of homomorphisms, and so this means that this map is etale finite. So gamma is and so the invariance of the big ring by gamma is just a small ring. And we can construct a tori like this. So we can construct group of, so let M be as before, finitely generated abelian group, and let be given a group morphism from gamma to the group of automorphism of M. Okay. Then gamma acts the group algebra over R prime by gamma acting on an element Rm. So this is gamma of R, gamma of M. So here and from now on, I write M instead of. Okay, so for brevity here, I denote simply by M the basis element that I previously denoted by E sub M. Okay, so you have the natural action of gamma on the ring, and you combine it with the action of on M given by this morphism of group. Okay, and so let's call this Hopf algebra, let's denote it by B. And then we can consider the invariant subring. So the elements which are invariant for the action of gamma is a Hopf algebra over R. And so if we set H equals spec of R, is a group scheme over S, which is the spectrum of R, and it is of multiplicative type. So indeed, by what is called Galois descent, so let me give a reference. Well, it's one among another. So so this can be one reference that I found in the book Nero Model by Bosch, Lütke, Baumert, and Renault. And so this is okay. So Galois theory in the Grothendieck form says by Galois descent, we know that one can recover B from A. So this is just A tensor over A by A prime as Hopf algebras and gamma modules. Where, of course, on the right-hand side, gamma is acting on this factor only. Okay. And therefore, thus, we obtain that if we make Bayes change, H from S to S prime, so this is spec of A or times R prime. And so by the previous isomorphism, this is just spec of R prime of M. And so this is our diagonalizable group, dm over S prime. Okay. So this Galois construction gives us hence our H is of multiplicative type M, of type M over S. Okay, so we can construct groups like that. And let me give you two examples, or at least one example, to show that this is not a trivial construction. That is, the group that we obtain is not diagonalizable, but it becomes so after a finite Galois extension. Okay, so first, so it is basic, but already instructive. Actually, we will come back many times in the sequel to this example. So in my notes, it has the number 1.5, so I just put this to record. So consider just the extension R, the field R into C. So it's Galois with, so gamma has two elements. let us denote by, so of course, tau is a complex conjugation. Tau of a complex number is just the complex conjugate. And the morphism from gamma to that Bruce. So which sends the non-identity element to -1. Okay. Oops, sorry. Okay, so this means that gamma acts. Well, so this means that gamma acts on Z, and the trivial elements send each integer n to its negative. N goes to -n. Okay, and so we have our, so gamma acts on the big algebra B, so which is the group algebra of Z over C. So this is just a Laurent polynomial ring by so tau acting on an element Z t to the m is complex conjugate of Z times 2 to the minus n. Okay. And one sees that then A, which is the algebra of invariant. So one sees that it is generated by two elements. So X is T plus its inverse. And to make things nicer, I divide by 2. And Y, which is, which one should I take? So T minus T inverse divided by 2I. Okay, so this is invariant because if I apply tau, these two are switched, so there is a sign of a change of sign and also at the denominator. So this is invariance. And so the 2 is just to make things nicer. And actually one sees that and one sees that A is the free polynomial ring C of xy divided by the relation x2 plus y2 minus 1. Okay. So this is the reason for the 2's, because otherwise it would have been 4, which is not nice, or it's better to divide by 2. Hmm? Hmm? Yeah. Thank you. This is an algebra. Thank you. Okay. And well, so it represents the functor. That takes any algebra over the reals. So let's call it R. The group of elements Z equal I plus IB in art and such. Such that Z times Z conjugate, that is A plus EB, A minus IB. So this is equal to A2 plus B2 equal to 1. Okay. So this, so we have this nice Hopf algebras, and it represents this function. And so in particular, the group of points with the C points are just the torus, the circle group in C. Okay. And so it is not diagonal, and so okay, so this group is not diagonalizable. Over S equals spec R. In fact, one can see that as a set of morphism of Hopf algebras, so we can ask which morphism of Hopf algebra from the coordinate ring of the split torus into A do we have? And there is only the trivial morphism. So there is only the trivial one. So we have the evaluation map, then goes to the real, and then the inclusion into R. So this means that the only if we look at the morphism of groups between H and the multiplicative group, well, there is only the trivial morphism. It is the one that factors through the trivial group. Okay, so it is an example of a group of multiplicative type, which is not diagonalizable, but which becomes so after a base extension. And well, okay, and so we have, and so we have all these examples. So whenever you have a Galois covering and a map from the Galois group to the automorphist group, so you can construct a group of multiplicative type. Okay. So now some remark. Yes. So so of a connected base, well, so let me rather put it in a, so if S is connected, normal, locally noetherian, one has the following theorem, which is difficult, and which we will prove later. And then every S group of multiplicative type is isotrivial. Okay. So if we work over a base which is locally noetherian and normal, for example, smooth, then there are no other example of groups of multiplicative types than the ones that you will obtain by Galois descent. We will give also example to show that this is not the case if the base is not normal. And of course, connected is essential, because if the base is not connected, so if you base as 2 points, both a spectrum of an algebraically closed field, so you can take a group corresponding to, you just take 2 different groups, so M1 and not isomorphic with M2, and so you have a group over your base which is not diagonalizable, because there does not exist a single M that works for both, but it is locally diagonalizable. That is, this point has a neighborhood itself over which it is diagonalizable, and so is this one. So locally diagonalizable makes sense of a non-connected base. But well, we could say we forget about non-connected bases. But so really the gist is what can happen over a connected base. Okay, now to proceed, I have to say a few words about representations of diagonalizable groups. So the foregoing was section 1 definition. Now this is section 2, which is called representations of diagonal visible group. Yes. And so first definition. So let G be an affine group scheme of S. And so it is endowed with multiplication R. So first, since it is affine, so it is given by a sheaf of quasi-coherent algebras A of S. And so we have the co-multiplication map from A to A to the tensor product, and also the augmentation map. And we also have an antiprod, but we won't be using it for what I want to say. And while they satisfy some action, so satisfying. So let me write them for one time. So if we apply the multiplications, then we land in this one. And from this one, we have two ways to go to the triple tensor product. We can take the identity and delta. And so this is the same as identity and so delta. So this corresponds to the associativity of the group multiplication. And we have, so if we start with delta and we go to this one, we can, if we contract one factor with epsilon, so if we apply epsilon here, so we are back to OS. And so this tensor product is just A itself. So this is the identity map of A, as well as if we do it like that. Okay, so we have these two properties that maybe we will be using in an instant. Now let's F be a quasi-coherent OS module. So we say F is a G module if for the I put the explanation here. Well, no, I just give the formula. If F is endowed with a structure A of right A comodule, that is so we have that is an OS linear map. Call it mu sub F that goes to F tensor product with A such that so if we take identity of F tensor epsilon and mu F, this is the identity of F. And if we take mu F a second time identity of A mu F, so this is the same as identity of F times delta times mu F. Okay, and again, this is the same as saying just a remark. This is the same. As let's say that for any S prime over S, the group G of S prime acts on the global section S is OS prime in the functogram. Okay. Maybe I should say okay, so this is a module over the ring of global functions on S prime. And so we have a linear action of this group and this. So if, but again, by Yoneda lemmas, it's translated into these two properties of comodule. Because I have written A on the right, and this corresponds to a left action. Thank you for that. And there is an analogous notion of left module, which corresponds to left action, to right action of the group. The group acts linearly on the left. Okay, so this is just a matter of notation. So if we want a left action of the group, it's better to write things like that. So let us try to prove one theorem now. Well, so now assume, so let G be a diagonalizable group and let F be quasi-coherent G module. As before, so we have this multiplication, we have this correction map that goes from F to F tensor OS. So this means this. So this means that for any affine open U, so we have this map from the sections of F over U to the sections of F over U tensored over this. And now, so what is this? So this is the direct sum of all M over M of the OS of U. Okay, so we can write that for any section X here, so we can write that its image, it's a sum of all M of M of, Let me write it here. So for all section, we can write that mu f of x is a sum for all m if m of the coefficient, which I will call Pm of x time the generator m. Okay, and for each x, it's a finite sum. For some OS linear maps, PM from f of u to OS of u. Okay, and I forgot the tensor product sign here. Okay, so now we will just apply this formula. Then okay, I will finish at 5. Okay. Okay, so let me just okay. Okay, so yeah, so I was so the PM of x are still in f of u. So if we apply it again, so if we apply this one, so we obtain a double sum for all m and n prime of m. So if we apply to this one, so we get p m prime of p of m tensor m prime tensor m. And if we apply delta to this one, we get just the single sum. And so we get that the composite PM prime PM is 0 if m is distinct from n prime, and PM squared is PM. So we have orthogonal. So we have orthogonal projectors of the module f of u with and then their sum is the identity by the first property. If we apply this, we just get the sum of the PM of x, and this has to be equal to x. So what does this say us? So we obtained that f of u is a direct sum for m of the image of PN. And so let us write this. So let's call the FM2. FM of U is a set of those sections X such that mu F X is equal to X and something. Okay, and so we and so we have. No, mu is mu originally is a coaction, so it is a sum. Yeah. Okay, so, yeah. So this means actually this corresponds to the M white space in a sense. So it is just a sum of white space, and so this is actually the direct sum of these subsheaves, and this is M grading on F of U. Okay, so I will finish with the theorem. So a structure of D to MS module on F is the same thing. As M grading. That is, we have a decomposition of a direct sum decomposition into locally free direct sum and parameterized by M. Okay, and I stop here, but just one word before finishing. I've been very careful by choosing an open affine, and then this direct sum is really a direct sum of modules. And one has to be careful that when you sheafify, so this sheaf is just the sheafification of the pre-sheaf defined by this. Okay, so sheafification that does not commute with direct sum. So this means that well, if you do well, yeah, one has to remember this, because I was well. If you don't restrict to an open affine, so well, it's not the direct sum. You have to take the product, and inside the product, you take those sections that are locally finite. So it's nasty to write in general. So it's better to do it over an affine or quasi-compact subset, and then everything works fine. And just one has to keep in mind that, yeah. So the triggered example, if you take a disconnected basis, a number of copies of spec C parameterized by M, and over each fiber you let so you can define FM to be the sheaf of section over the M copy. Okay, and so the global section over this disconnected space is just the product sheaf. But locally, if you take a quasi-compact subset around many points, and also it is yeah, exactly. Otherwise, you have to be aware what is the meaning of a direct sum sheaf. Okay, now I will stop here.